In order to increase food production, the total amount of food which is produced, essentially three ways of doing that. Either you increase the arable land which you have, or you increase the crop intensity, which means that you plant more times per year, or you increase yields, right? If you look at the available land, the available arable land, there are different numbers out there, but consensus is pretty much that it is very difficult. We will not have much more additional land where we can plant in. If you look at crop seasonality, that is defined by climate. So that is not going to change significantly. It's not that you will be able to start, okay, I don't want this to go against climate change, but let me see how I can formulate that. If you look at crop seasonality, that is not expected to significantly change over the years. Essentially, you will not be able to plant more times per year in any given location of the world. If you now look at crop yield, there are different ways of doing that, right? In highly developed countries, such as in the US, and this is why people are very much looking to precision agriculture, for example, we are already producing at a very high yield, right? So any additional, and we have all the fertilizer, we have a big part of the fertilizer that we require, so it's mostly about fine-tuning and making sure that you can really extract all that you can out of that soil. In underdeveloped markets especially, so Africa and Southeast Asia, the problem is not precision agriculture, but rather the problem is that you don't even have sufficient nutrients there in order to grow your crops. So you don't have enough, the soil is still of very low quality because people have not been able to correct it fully, and also you don't have the required nutrients which you need in order to make that plant grow in the first place. So looking at that, the solution to be able to tackle the food problem is really looking at much further upstream, which is looking at the fertilizer industry itself and trying to find a way of providing those farmers with nutrients. And given you have a significant population increase, nowadays we have roughly 7.2 billion people on the planet. By 2050 that is expected to increase by to call it 9.2 billion people roughly, and even more so by 2100. There is a natural demand of food, or a natural increase of the food demand which is going to occur. Even more so, there is a trend of people wanting to eat more and more meat when a country develops. That creates a significant demand on food, because you will then have to feed those animals to then be able to eat. You will have to feed those animals with grains and other types of crops to then be able to eat that protein. And these two factors together are expected to have a significant impact on demand for crops. Since the beginning, we realized and we knew that in order for this technology to be able to be adopted on a worldwide basis, it had to be cost efficient, right? It would not be sufficient for you to produce a high quality fertilizer, which then cannot compete with the existing product out there. And this is why when we started working on the technology with MIT back in 2012, our directioning and our boundaries, economic boundaries, were also always given in a way to make sure that we can, at the end of the day, compete. And this then resulted in a low temperature, roughly 200 degrees C, and therefore low pressure hydrothermal process. And given the low temperature, the energy usage is not significant, which then helps you to remain at low cost. The concept of trying to extract potassium out of feldspar is not something novel, because feldspar, the same thing that we did, looking at the earth crust and seeing where the potassium is, people have done that in the past, and it was always very much in people's faces and very apparent that feldspar is the ideal source and also by far the most abundant source of potassium out there. Where we differ from others, and this then also leads very well in why our costs are lower, is that as opposed to trying to extract and separate the potassium from the feldspar, which inevitably requires very high temperatures and pressures and therefore implies high costs, what we did is we try to disrupt the crystalline structure just enough to make that potassium available, but not extract it fully. And another reason why we also did that is whenever you try to extract potassium out of feldspar, you're inevitably, as I said, bound to high temperatures and pressures, which mean high costs, but also you have material which you will then not use. So you will have to see, okay, what am I going to do with the excess material and with all those byproducts? In our case, feldspar, the vast majority of feldspar is actually silicon, which is very good for plants. It's also a nutrient. Why would we spend money effectively and time to extract something which at the end of the day is also liked by plants? So this is why we developed our process in a way where we only disrupt the crystalline structure, we make the potassium available, and we leave all the other nutrients which are also good for plants, such as silicon, we leave that in there. And then we provide a product to the plants which is not pure potassium, but is potassium plus other nutrients as well.